Hi class, nice to meet you again. So today we will go to the lesson number 3. I hope you already studied the lesson 1 and lesson 2 that I uploaded 2 weeks before. And now we go to the third lesson. And it just announced by the university, maybe in April we still have to study by the online. That means I have to continue to teach and record the video and upload in the BK e-learning, and you have to learn at home. We have to continue this in April. So now we go to lesson number 3. This is the second law of the thermodynamics. In the previous lesson, we already learned the first lesson. So in this lesson, there will be 5 main parts. First, it is about the second law of thermodynamics. Second, about the heat engine. Third one is the refrigeration system. Number 4 is the Carnot cycle. And number 5 is the Carnot theorem. Okay. In your last lesson, you learned about the first law of the thermodynamics. And the first law of thermodynamics here, we just call in shortcuts. Short form is LTD1. It's the law of thermodynamics number 1. Perpetual motion machine. What is a perpetual motion machine? I mean, in the past, a lot of scientists try to create the machine that it can run, or we can call perpetual. That means forever. Okay, that means forever. That means they try to create a machine that can run forever, non-stop, without any provide the heat or any kind of external energy into the machine and make it work forever. So they call it a perpetual motion machine. Based on the first law of thermodynamics, there cannot be a machine which continuously supply mechanical work without some other form of energy disappearing simultaneously. Okay? It means in order to provide the mechanical work, you need to provide the external form of energy in other form of energy, either in electrical or in mechanical, etc. That is the first law of the thermodynamics. So, as I call this, is some fictitious machine. I mean, the machine that the scientists try to create. The perpetual motion machine of the first guy, we call it briefly, is a PMM1. So based on the first law of the thermodynamics, they say that it is impossible to create the PMM1 machine. Okay? But then after the scientists, they couldn't create the PMM1 because they agree with the first law of thermodynamics. They tried to create the PMM2. So PAM2, what is the PAM2 work. So look at the formula of the first law of the thermodynamics. Q equal to W plus delta U. So they say that without the Q here, for the first law of thermodynamics, without the Q here, you cannot create W. So this is about the first law of thermodynamics, and that is about the PMM1. But the PMM2, they look at the formula, they saying that, okay, I agree that there is the relationship between these three kind of energy. But now, if in somehow I can make the WU become the useful energy, so in this case, we still can have the form of the energy. I mean, we got this formula is like this. That is the formula of first law of energy. And now they say that if Q equals 0, so in this case, we got W equal to minus delta U. That means they say that somehow if I can make this become the useful energy, I still can create the work without the energy from the outside. So look at this formula. The first law of thermodynamics cannot explain why this cannot be happen, because you see that in the formula, in the mathematical way, we still can do that. But in reality, it cannot do it. So we need the second law of thermodynamics to explain why the PMM2 is impossible too. Okay? Or look at this example. The first law of thermodynamics doesn't indicate the direction of the process. That means in the natural, there's only the natural direction. But if you want to do in the opposite direction, either it's impossible or you need to provide the external energy. Look at the example. For the hot coffee, of course, you know that the heat can transfer from the hot coffee cup to the outside temperature. That is just the natural direction. But it's impossible that you can transfer the heat from the surrounding to the hot coffee without consuming any kind of energy. So this one, the first law cannot explain, because there's no, in the first law of thermodynamics, it doesn't show the direction. Or in the second picture here, you see that, for example, we got the stirring machine here is run into the water, and if it's do that, later on you can see that the water is become warmer. That means the work is transferred into the heat to make the water is warmer. But it's impossible that you can make the heat here to run the stirring machine. That means the heating water cannot make the shaft rotate. But again, the first law of thermodynamics cannot explain this. I mean, there is the way to transfer from the work to heat, but in the opposite way. There is not the natural way, and the first law of thermodynamics cannot explain. So it means to make the process occur, that both the first law and the second law need to be satisfied. So that's why we need the second law of thermodynamics. So there are two statements for thermodynamics. The first statement we call the Kelvin-Planck statement, or the heat engine statement. That means this statement is applied for the heat engine. In the first lesson, you already familiar a bit what is heat engine is and what refrigeration system is. The heat engine, like the motorbike or the internal combustion engine, that is the heat engine. That means it transfers from heat to work. That is we call the heat engine. And other form of the machine that we study in the thermodynamics, that is refrigeration. So the refrigeration is, transfer the heat from the colder place to the hotter place with the supply of the external energy. So the Kelvin-Planck statement is applied for the heat engine statement. It's saying that it is impossible to devise a cyclical operating device, the solely effect of which is to observe energy in the form of the heat from a single thermal reservoir, okay, and to deliver an equivalent amount of work. Look at this example. That means, in this case, the heat engine only works with one reservoir. It is the heat source. It not release the heat to the coal sink. Okay? So it's saying that it is impossible for the heat engine working only with one single thermal reservoir and provide the work. If this exists, it means the work it produced by the heat engine will be equal to the amount of heat received from the hot source, and in this case the thermal efficiency will be equal to 1 or the 100%. So it means that it's impossible to build a heat engine that has 100% of the thermal efficiency. So it means impossible to do like this. All right. And again, I want to give you the example that I will give you in the first lesson to you to remember what's the heat engine is. It is the motorbike or the internal combustion engine. Or other example like the thermal power plant or the electrical power plant. I mean, in this case, you see that it produces the steam, and the steam here run the turbine. The turbine run the generator, and the generator will generate the electricity, and it just transfer into the electrical line. So it is another example of the heat engines. And now for the thermal power plant, this is a diagram, the simple diagram of one thermal power plant. Is first, we got the boiler here, we call the steam generator. It receives the heat from burning the fuel, for example, the coal or the oil or even the nuclear, etc. So it means it's provide the heat to the boiler, and the boiler will generate steam. The steam will go into the turbine, run the turbine. The turbine here is, run the generator. It means it produces the work out. And then the steam will go down to the condenser, release the heat W out to the coal sink. And after that, it becomes the condensate. The condensate will be pumped back to the boiler. It's a complete cycle, and the cycle continues. And this picture you already familiar in the first lesson. That means in order for the heat engine work, it needs work in the two reservoirs. It is the hot source and the coal sink or the coal source. In detail, it receives the amount of work in, the Q in from the hot source, release a small amount Q out to the coal sink, and it's produce the work W. And in order to know how well the thermal power or the heat engine work, they use the thermal efficiency. So the thermal efficiency here will be equal to mu equal to W out minus W in divided to Q in. And because the work consumed by the pump is very small compared to the work produced by the turbine, so we can ignore the Q in. So in this case, mu equal to work out, W out minus divided to Q in, and it's equal to 1 minus the Q out divided by Q in. And as you already know that if the heat you receive, it have the positive value, and the heat you release from the system, it have the negative value. So in this case, Q out, it is a heat released from the system. It have negative value. So in this case, we just consider the absolute value. So we use absolute symbol here. So it means the mu here equal to 1 minus Q out divided by Q in. And based on the Kelvin and Planck statement, it's saying that Q out here must be different from 0. So it means this Q out divided by Q in must be bigger than 0. So it means mu here must be smaller than 1, or it's smaller than 100%. So this is the Kelvin statement for the first law. And look at the example is violate the second law of thermodynamics. For example, we got the thermal power plant, but we don't have the condenser here. So it means there's no heat release from the system. So it means in this case, the steam provided to the turbine create work, and after that, the steam will go back directly to the pump, and it go to the boiler. It is impossible because this is, only work with the one energy reservoir. So this violate the second law of thermodynamics. If the Kelvin and Planck statement is applied for the heat engine, the closest statement is applied for the refrigeration system. It's saying that it is impossible to construct a device which operates on a cycle and produce no other effect than the transfer of heat from a colder body to a hotter body. Okay, so you look at the picture here. So it means the refrigeration system receives the heat from the cold sink and release it to the hot sink without receive any external work. So again, this is impossible. So that is the closest statement is applied for the refrigeration and heat pump. Look at the example of a refrigeration. All right. So we got 4 main elements in this compressor: the condenser, expansion valve, evaporator. So the compressor here first it will compress the air, the refrigerant, or we call the gas in the system in high pressure and high temperature. Go to condenser. In the condenser is release the heat to the hot source. It will be condensed, and the condensate go to the expansion valve, and it will reduce the pressure from state 3 to state 4, and from state 4 the refrigerant or the gas will go to the evaporator. It will be evaporated and is observe the heat from the cold space, and after that it go back to state 1 and it complete a cycle, and the next cycle will continue. That is the principle of refrigeration system. Example, we got refrigeration, for example, a refrigerator. You know that at the refrigerator the evaporator here is inside inside the refrigerator, and the condenser normally is in the back of the refrigerator, and definitely it got the compressor. They call it a block here to to pump the air. So we got the gas will be compressed in the compressor, go to the condenser, and at the condenser is release the heat to surrounding, and it's go to the capillary tube. In the capillary tube here, it is the expansion valve, and after that the gas will be reduce the pressure, go to the evaporator, and at evaporator it absorb the heat and come back to the compressor. The second example, we got like air conditioner, and two kind of air conditioner you usually have at home. They call the window air conditioner and the split air conditioner. The window, because this look like the window, so they call the window air conditioner. And the second kind of the split time, I mean they split the evaporator and the condenser in the two unit, so they call the split here. I mean they split, it means divide, and they got the indoor unit. I mean you put the evaporator in the room, so they call it indoor unit. And the outdoor unit here, I mean we got the condenser, and the compressor is you put outside, so what they call the outdoor unit. And look at the diagram here. Of course, it's got so many things, but you don't worry. Just look at the outdoor unit here. It's including the condenser and the compressor. They put outside the room, and inside the room we got the evaporator. They got so they connect by the tube here, a small tube they call a capillary tube. Play the role as the expansion valve in the system. Okay, so this one is the example of the air conditioner. We got again for this one you have to make the hole in the wall and put the air conditioner in, and you got the indoor and outdoor. Of course, as you know that all kind of machine, including a heat engine and refrigeration, have to work in the two reservoir. Is they call the hot source and a cold sink. And inside, of course, we got the cooling coils here, and in order to increase the heat transfer, they use the blower in order to move the air faster to increase the heat transfer procedure. For the outdoor, you got the condenser, coil, and the compressor. Okay, and again they use the fan here in order to push the air go through the condenser faster, and it's make the heat transfer coefficient increase. So again, you also see that is the indoor unit and outdoor unit, but it make one block. But in the split time, they just split here, make one indoor and make one outdoor. For the refrigeration, we also got four main parts. That is the compressor, condenser, expansion valve, evaporator. Okay, and here we again for the heat pump and refrigerator, they have to work in the two reservoirs. They did hot source and a cold sink. It means it's absorb the heat from the cold sink, release to the hot source, and in order to do that, it must receive the heat from the outside, W. And in order to know how well the refrigeration system works, they use the concept of the coefficient of performance, and they call in short form it the COP. For the refrigeration system, is epsilon is the COP, but the epsilon equal to Q2 divided by W. You know, because for the refrigeration or for the air conditioner, the amount we consider, that is W2. That means the amount of the heat it absorbed from the cold sink. So this is useful energy, and the energy that we need to provide. I mean the work, and you learn in the first lesson that the work is produced is have the positive value, and work received it have negative value. So in this case, because this work you receive or the compressor is consumed the work, so we got the negative value. We just consider the absolute value, so we just use the absolute simple. So it's equal to Q2 minus for Q1 absolute minus Q2. And again, the heat is released, that is have a negative value. So Q1 in this case have negative value, so we put Q1 in the absolute simple. For the heat pump, it works the same principle of the air conditioner or the refrigerator. Just the different that in the air conditioner we need the cold. It means the evaporator we put in the room. But for the heat pump, we need the hot air. I mean in the winter time, instead of they just use the normal resistant heater, they will use the heat pump. In this case, the amount of the heat released from the condenser, that is become the useful energy. So in this case, the COP, or the coefficient of the performance of the heat pump, will be defined by phi equal to Q1 divided to W. So in case of refrigeration, you see that it is a Q2, because of different energy that you use. So in this case, again, Q1, because it's a heat release, so it have negative value. So we put in the absolute simple, and W, because this is the work received, so it have negative value, so we use the absolute simple. Okay, so you say that there is two statements that apply for heat engine and the refrigeration in the second law of the thermodynamics. Now we can see that even though there are the two statements, at the first sight you think that this is different, but in reality it is connected. Okay, so in other words, the Kelvin planes and the closest statement, actually that is the two parallel statements of the second law and equivalent in all respects. The equivalence of the two statements will be proved if it can be shown that the violation of one statement implies the violation of the second, and vice versa. Okay, look at the first example. Consider a cyclic heat pump P, which transfers heat from a low temperature reservoir T2 to the high temperature reservoir T1 with no other effect, or it means with no expenditure of work. This one definitely is violating the closest statement. Okay, I mean it transfer the energy from the low temperature reservoir to the higher temperature reservoir without any other form of energy supply. That is definitely violate the closest statement. Now we will prove that this also violates the Kelvin blank statement. Alright, so you can look at this picture. This is the heat pump P. It work in the two reservoir. Is a cold reservoir at the T2, and the hot reservoir is T1. And now assume the cyclic heat pump E. So we again put the heat pump here, heat engine here also is E, operate between the same energy reservoirs, produce work net W net equal to W minus equal to Q1 minus Q2. The rate of the working of the heat engine drawing from the hot reservoirs Q1 equal to that discharged by the heat pump. Then the hot reservoir may be eliminated and the heat Q1 discharged by the heat pump is fed to the heat engine. Okay, you look at this example. It means in this case, because the amount of the heat here, Q1 equal to Q2. So in this case, instead of they have to receive the heat Q1 from the cold reservoir for the heat pump. In this case, we receive that amount directly from the heat engine. So in this case, to see if it's work or not. So the heat pump P and heat engine E acting together constitute a heat engine operating a cycle and producing net work Y exchange only with one body at a single fixed temperature. Okay, so you see in this case, because it received directly the heat from the heat engine, so is there the second reservoir, so it only works with one reservoir. So this one violates the Kelvin-Planck statement. So this, you can see that actually when it violates the Clausius statement, it also violates the Kelvin-Planck statement. So you can prove that these two statements even is different in definition, but it is the two parallel statements of the second law of the thermodynamics. Go further, we go to the second example. Consider the PMM1. You know what the PMM1 means. Is a perpetual motion machine type number 2. So now consider a PMM2E, which produce network in a cycle by exchanging heat with only one thermal energy reservoir. Okay, so for the PMM1, for PMM2, it just work in a one thermal energy reservoir at T1, and of course, if it's work only one with one reservoir, it violates the Kelvin-Planck statement. Assume the cyclic heat pump P extracted heat Q2 from a low temperature reservoir at T2 and discharging heat to the high temperature reservoir at T1 with expenditure of work W equal to what the PMM2 deliver in the complete cycle. All right, so you look at the picture here. That means this one is PMM1 because it's only work with the one reservoir. There's no heat released to the cold sink. So here's Q2 is equal to 0. So definitely it's violate the Kelvin-Planck. So now we prove that it's also violate the Clausius span. So in this case, for example, we got the heat pump put with this one. So it means instead so the cyclic heat pump P extract Q2, okay, Q2 from the low temperature at the T2 and discharge heat at the high temperature reservoir, this one. But instead of receive the work from outside, in this case it will receive this kind of energy is is Q1. That means the heat received from the PMM2. W is EMM equal to 0.1. So you see that the PMM2E and the heat pump P together constitute a heat pump working in a cycle and produce the sole effect of transferring heat from a lower to a higher temperature body. So thus it violates the clauses statement. So you can see that in this picture, the heat pump doesn't receive any outside work, but only it's received the heat from the PMM2. So this one is violates the clauses statement. So the second example is proof that when one machine or one cycle, it violates the Kelvin-Planck statement, it also violates the clauses statement. So it's again, you can say that the Kelvin-Planck and the clauses statement, it is the parallel statement of the second law of thermodynamics. Okay, now we go to part 4. This is a Carnot cycle. Reversible and ideal process is one which is performed in such a way that at conclusion of the process, both the system and the surrounding may be restored to their initial state without producing any change in the rest of the universe. Okay, so for example, look at the picture A. First, this one is the system, and as you know that system and this one is surrounding, and it will be separate by the barrier. In this case, for example, we got when it's for example is in the first process from A to B, it produces the work WAB, and when in the reverse process, that means it go from state B to state A, it will receive again the work WBA, and because WAB equal to WBA, so in the reversible or the ideal process, there is no change in the environment. I mean the end of the two process AB and BA, there is no change in the surrounding, and it will restore the initial state. So of course, this one, the reversible and the ideal gas, it's not exist in it's a real. So in reversible or the natural process carry out with the finite gradient, the irreversibility of the process may be due to either one of the both reasons. Either it's because the lack of equilibrium during the process or the involvement of dissipative effect. Okay, so what's the equilibrium and what is the dissipative effect? You can look at the chapter I provided to you, because in the lesson we got the very limited time, so I don't explain in detail, but if you want to know, you can learn more in the materials that I provided to you. So a reversible cycle is an ideal hypothetical cycle in which all the processes constituting the cycle are reversible. Okay, so when all the process is reversible, they make a reversible cycle. It's combined of all the the reversible processes. So the Carnot cycle is a reversible cycle. For a stationary system, as in a piston and a cylinder machine, the cycle consists of the following 4 successive processes. Okay, so there are going to be the 4 processes as follows. First is a reversible isothermal process. Isothermal is the process that have the constant temperature, as you learned in the first lesson. Huh? So a reversible isothermal process in which Q1 enter the system at T1 reversibly from constant temperature source at T1 when cylinder cover it in a contact with the diathermic cover A, and the internal energy of the system will be increased. So from the first law we can write it Q1 will be equal to U1 minus U2 plus W12. The next process will be the reversible adiabatic process. So the adiabatic process, that means the process have the entropy S is constant. So this in which the diathermic cover A is replaced by the adiabatic cover B, and work WE is done by the system adiabatically and reversibly at the span of its internal energy, and the temperature of the system decreases from T1 to T2. And based on the first law, because the adiabatic, that means the process, there's no, or we can call this adiabatic, that is the thermal isolated system. For the thermally isolated system, you get familiar in the first lesson. So it means for the adiabatic process or the thermally isolated system, Q equals 0. So in this case we got the Q is 0, equal to 3 minus 3,2 plus the W23. The third process is the reversible isothermal process in which B is replaced by A and heats Q2 leaves the system at the T2 reversibly to the constant temperature sink at T2, and the internal energy of the system further decreased. So based on the first law, we got minus T2 because the Q2 is the heat release the system or the leave the system, so it's have negative value. So we got equal to for U4 minus U3 minus W34. And the fourth process is the reversible adiabatic process in which B again replace A and the work WP is done upon the system adiabatically, and the internal energy of the system increase and the temperature rise from T2 to T1. And from the first law, again, because it is by adiabatic, it is isolated, thermally isolated, so Q equals 0. We got 0 equal to U1 minus U4 minus U41. So two reversible isotherms and two reversible adiabatic constitute the Carnot cycle represent in the PV coordinate. Okay, so we got 1, 2, 3, 4, 1 here. Okay, so we got 1, 2 and the 3, 4 we call the reversible isotherm, and 2, 3 and 4, 1 that is reversible adiabatic. Okay, so sum up from equation 1 to equation 4. Finally, we got Q1 minus Q2 equal to W12 plus W23 minus W34 plus W41, or the total cycle of the Qnet equal to total of the Qnet of the cycle. All right. So for the that is we talk for the system. Now we talk for the steady flow system. The Carnot cycle is represented in the picture here. Again, it's similar to the thermal power plant as we just explained before. Here we got the turbine, we got the cold sink, that means the condenser here, we got the pump and the heat exchange here, that means the boiler here. So it is the four main basic components of a thermal power plant. And in this case, we got the system boundary, that this one. And in this case, the system boundary will be separate the system with the surrounding. To satisfy the condition of a Carnot cycle, there must not be any friction or the heat transfer in the pipeline through which the working fluid flows. So heat W1 is transferred to the system reversibly and isothermally at T1 in heat engine A. Okay, heat engine A here. Work WT is done by the system reversibly and adiabatically in the turbine B. All right, and then the heat Q2 transfer from the system reversibly and isothermally at T2 at the heat exchange C. All right, and work WP is done upon the system reversibly and adiabatically by the pump D. All right, so there is a four process in 4% in the Carnot cycle for the steady flow system. So the reverse heat engine, the reversible Carnot cycle for the steady flow is shown as this picture. Okay, so it's same the previous picture, but it's go in the reverse direction. Okay, so in this direction you can see that go into the clockwise cycle, but in the next picture is so in the anti-clock cycle, go in the opposite way. So we call that reverse heat engine. When a reversible process is reversed, all the engine transfer associated with the process are reversed in direction but remain the same in the magnitude. Okay, so it means we got the complete opposite cycle. The reversible heat engine and reverse Carnot heat engine are represented in this picture. Okay, so A here is the reversible heat engine, and the B is the reverse Carnot heat engine. You see it exactly the same, but it's just in the opposite direction. For example, for the heat engine, we got the Q received from the hot sink and release Q2 to the cold sink. But in the Carnot reverse heat engine, it will receive Q2 from the cold source and is relieve Q2 to the cold for the hot source. All right, and in the reversible heat engine, it receive the WP and produce WT, and W net equal to WT minus WP. But in the reverse Carnot heat engines, it will receive WT, it produce WP, and W net will be WT minus WT. The heat pump and refrigerator are applied to the reverse heat engine, where the working fluid flows through the compressor B, condenser A, expander D, and the evaporator C to complete the cycle. So now we go to the fifth part, that is the Carnot's theorem. All heat engines operating between a given constant temperature source and a given constant temperature sink, none has a higher efficiency than a reversible engine. A reversible, I would call the Carnot engine here. In other words, the Carnot engine or the reversible engine have the highest efficiency. There's no real engine have the higher if they work in the same two temperature reservoir. Look at this. Look at this picture. We got two heat engines, EA and EB, operate between the given source T1 and the sink T2. So let EA be any heat engine and EB be any reversible heat engine. We need to prove that the mu A will be smaller than mu B. So you know the mu B here is, that means, reversible heat engine, and mu A, that means is the efficiency of the real heat engine. So now assume that in the opposite way. Okay, we assume that mu A is bigger than the mu B. So in this case, the rate of the working of the engines will be Q1A will be equal to Q1B equal Q1. Since mu A larger than mu B, so we got WA divided by Q1A will be larger than or bigger than WB divided by Q1B. So it means WA is bigger than WB. So let EB be reversed. Since EB is a reversible heat engine, the magnitude of the heat and work transfer quantities will remain the same, but the direction will be reversed. Since WA is bigger than WB, so some parts of WA equal to WB may be fed to drive the reverse heat engine. Okay, so it means this produces a because WA here is bigger than WB, so WA here is used to fit the reverse cycle EB. But we already know that W1A equal to W1B equal to Q1A equal to Q1B equal to Q1. The heat discharge from the reversible heat engine EB may be supplied for the EA. Therefore, the source may be eliminated. The net result is that the EB and the EA and EB together constitute a heat engine which operate in a cycle, produce a network WA minus WB, while exchange heats at the single reservoir at T1. Okay, again in this case, because the heat is transferred here, so we can eliminate the hot reservoir and it's only work with one single reservoir, and this violates the Kelvin-Planck statement of the second law. So hence the assumption of the mu A larger than or bigger than mu B is wrong. So definitely mu A must be smaller than mu A. I mean, efficiency of a real heat engine must be smaller than the reversible heat engine or the Carnot heat engine. Corollary of the Carnot theorem. The efficiency of all reverse heat engines operates between the same temperature levels are the same. They are independent of the nature and amount of working substance undergoing the cycle. If both reversible heat engine EA and EB working between the same hot source and a cold sink, we have mu A equal to mu B. Okay. The efficiency of the reversible heat engine The efficiency of the reversible heat engine in which heat is received solely at the T1 absolute is found to be the mu reservoir equal to mu max equal to 1 minus Q2 minus divide to Q1 for the reversible cycle will be equal to 1 minus the T absolute 2 divide to T absolute 1 or equal to T1 minus T2 divided by T1. When T2 decrease and T1 increase, the efficiency will be increased. That is for the heat engine. For the refrigerator, we got the COP. So the COP, we got COP for a refrigerator equal to Q2 divide to Q1 minus Q2 equal to 1 divided to Q1 over Q2 minus 1. And when T2 decrease and the T1 increase, the efficiency will increase. And for the reversible refrigerator, we got the Q1 divided to Q2 equal to T1 divided by T2. So the COP of refrigeration for a reversible system will be equal to T2 minus T1, T2 divided to T1 minus T2. Similarly, for the reversible heat pump, we got the COP for heat pump for the reversible system will be equal to T1 divided to T1 minus T2. So that is about the Carnot cycle, Carnot's theorems, and the efficiency of the Carnot reversible heat engine and the heat pump and refrigerator. Okay, and this is some terminology to help you to get familiar with the lesson. So please look at that, and again read the materials that I provided to you, and do the old exercise in the book. Okay, so goodbye and good luck, everybody.
Yeah.